Hi everyone, so we are live now, and this is going to be lecture number 40 on signal and system, right? So you can say this is the final part of Fourier transform, that is continuous Fourier transform, right? After that, we have got Laplace transform, jet transform, discrete Fourier series, DTFT, okay, and DFT. So these are the topic that is remaining, okay, after finishing the CTFT part, right? So this is nothing but a part, you can say five, okay. Already we have done many parts. So I think this is nothing but a part, part six. Okay, I must say part six. Okay. So in the last session, what we have discussed, we have discussed the question based on the property. So one of the very beautiful property we have got, that was nothing but Plancherel relation, right? Plancherel theorem or Parseval theorem. And so if we want to compute some integral, okay, involving Fourier transform, so it becomes very easy, right? And in the gate examination, you will find many questions from that. So I will take one more question today, and then we will cover all the topic which are not done at. Okay. So so let me take one question here. Okay. Based on that question, we will solve. You know, we'll use again the. Okay. So we have to evaluate one integral here. Let me show you that integral. Right. So this is the integral we have to evaluate. Okay. So what concept I have, okay, what concept I have told you, right? So you see here there are two signal again, right? So sync f e raised to power j pi f and 1 plus j2f, right? Okay, so you can also convert this into omega, but it's fine, it is given in f form. So we have to use the Plancherel relation, okay? Plancherel relation you have to use इन एफ फॉर्म ओनली, ठीक है. सो अब ये इंटीग्रल आपको सॉल्व करना है, तो सबसे पहले क्या रहेगा, व्हाट इज एक्स ऑफ एफ. सो यू कैन से एक्स ऑफ एफ इज नथिंग बट 1/1 plus j2 pi f, right? This is x of f, okay. I believe this is fine. And then you have to take y of f, right? So y of f, that too you have to take the conjugate of that. So y of f conjugate is going to be sync f, okay, e raised to power minus j pi f, right? Because they have given positive plus j pi f, but if you take the conjugate here, it becomes minus j pi f, right? Understood? So I believe this, I mean, you can just put star here, right? So understood. So I think this is clear, right? So if you take the conjugate of this, so it becomes okay. But and what is y of f? Y of f is nothing but sync of, okay, sync of f e raised to power, j pi f, right? Or you can directly say this is nothing but a conjugate, and if you remove the conjugate from here, I mean, if you take the conjugate of this, right, so it becomes positive one. Okay. So this is nothing but y of f frequency, because we have to fit into the Plancherel relation. Okay. So I think this is clear, right? So what you can do here is, now you can find out the inverse Fourier transform, right? Okay. So remember, this is nothing but y of f. Okay. And this is the, okay, we have to compare with the integral that we know, right? That is nothing but minus infinity to infinity x of f by conjugate of f df. Okay. So the given by f conjugate is given, right? So if you remove this conjugate, so it becomes minus. Okay. So I think this is clear. Now it is equal to, in time domain, we know that it is going to be from minus infinity to infinity x of t by conjugate t dt. Okay. So I think this is clear, right? So you have to find the Fourier transform, right? Inverse Fourier transform of x of this, right? So what is the inverse Fourier transform of this, right? So 1/1 plus j2 pi f, okay, which is nothing but having the inverse Fourier transform e raised to power minus t ut. Okay, I hope this makes sense. This is nothing but x of t, okay, from the known Fourier transform. And sync f, okay, sync f e raised to power j pi f has the Fourier transform, right? Sinc f has the Fourier transform, I mean inverse Fourier transform, you can say. So this is in frequency domain. So what is that signal whose Fourier transform is nothing but, whose Fourier transform is nothing but sinc function? That is nothing but what? You can say rect, right? So here we will put rect, okay, rect. And here you see this is plus j pi f, okay. So you have to shift it, because if something is multiplied in the frequency domain like exponential to the power j pi f, it means there is a time shift in the time domain, right? Okay, so this is nothing but you have to shift back, okay. So what is the shift here? You see this is nothing but t minus 1 by 2, okay, t minus 1 by 2. I hope this makes sense. Fine. Or what you can do here is, if you don't want to do like this, let me tell again. What you can write here is, that sinc of f can be written as sine pi f by pi f, right? Okay. And you can convert into omega, okay, because you know the omega form, okay. So you can convert into omega and get it back, right? So yeah, so sine pi f by pi f, okay, understood. So this is sinc of f. Now if you multiply this with the exponential e raised to power j pi f, so you can write this as sine pi f by pi f, okay, e raised to power j pi f. So what is the Fourier transform of this? This is nothing but rectangular, right? Rect, you can say rect t. Rect t means the width is from 0.5 to 0.5, okay, and this is 1. Okay. Now you have to shift, okay, in the time domain there should be a shift. And what is the amount of shift in the time domain? See, since there is a plus sign, right, so you have to shift, okay, this is j pi f, okay, j pi f, okay, so you have to shift it, right? So what is that shift? So you have to shift this by 0.5 to the right, okay. So if you shift this to the right, okay, so what is that? So you can shift this guy, so it becomes 0 to 1, right? Okay, so this is nothing but your by conjugate of t, okay, by conjugate of t, understood? Because of this exponential, we are shifting this signal to the right by 0.5, okay. I hope this makes sense. So you have got two signals, एक xt हो गया and एक ये हो गया. So we have to find the integration, right? So integration minus infinity to infinity xt times by star t dt. So we can draw this. So exponential is nothing but this, right, which is nothing but e raised to power minus t ut, and there is a, you can say, okay, this is one more signal, right? We have to multiply them. So this is 1 0 to 1, right? So you have to just multiply and find out the area. So I think multiplication, this is the common part, right? And then you have to integrate this from 0 to 1, right, because this is from 0 to 1, okay, and then e raised to power minus t dt, simple, right? So I think this is clear. So it is nothing but e raised to power minus t by minus 1 from 0 to 1, so it becomes 1 minus e raised to power minus 1, okay. Yeah, so this will give you around 0.6321. This is the answer for the question, okay. तो आपको क्या करना है, you have to just find the inverse Fourier transform, right, of given Fourier transform, right, and then you have to integrate it, okay, that's it. The common portion has to be integrated. You are finding the area of the common portion, okay. So I think this is clear, provided you should be good at how to find the Fourier transform and what is its equivalent. अगर मान लो कोई पूछता है इसका फोरियर ट्रांसफॉर्म क्या होगा, तो इसका फोरियर ट्रांसफॉर्म सिंक होगा, सिंक पाई एफ बाई पाई एफ ई रेज टू पावर जे पाई एफ, ठीक है. So I think this is clear. Next we have used Parseval relation, that's it, okay. There is a concept like, in Fourier series, we have studied about Dirichlet conditions. Okay, so in Fourier transform also there is a Dirichlet condition, you can say. So any xt will have the unique Fourier transform if you can say some points are there, right? So just I'm going to take this snapshot here, okay, and we'll show you. We'll talk about existence. देखो, existence, convergence, and uniqueness. The Dirichlet condition for Fourier series establish the sufficient condition for the existence of the Fourier series coefficient and, or you can say Fourier series only, and are based on the one period of the periodic signal. The same condition for existence also valid for the Fourier transform, provided they are now applied to entire extent of the non-periodic signal, right? So we are not going to focus on one period, right? Remember, in case of Fourier series, we were focusing on one period, okay? But here we have to focus on entire because we are finding the Fourier transform of non-periodic signal, okay? So these are the conditions. You see, these conditions may be restated as follows. A function C, what we are doing is we are modifying the Dirichlet condition what we talked about Fourier series है ना. Fourier series के लिए हम particular one interval में देखते हैं, okay? If for one interval everything is okay, so since as long as it is a periodic signal, right? So xt must be absolutely integrable, ठीक है? xt has finite number of maxima and minima and the finite number of finite discontinuity. If the Dirichlet conditions are satisfied, then if as f tending to infinite, the Fourier transform xt will converge to, okay, xt whatever it is continuous and piecewise differentiable, uniform convergence, and this is at the midpoint at the jump continuity, okay? So मान लो जैसे ये Fourier transform है x of f, so this is a jump discontinuity, right? So it will converge at the midpoint, okay? Understood? So I mean okay, the signal must converge, like signal must converge at this, okay? Okay. So these are just Dirichlet condition that you have to consider. That's it, okay? Nothing else. So uniform convergence and non-uniform convergence, okay? And one of the important class of concept that you have to learn, which is asked everywhere, that is nothing but system analysis using Fourier transform, okay? System analysis using Fourier transform, okay? So where you have to find the Fourier, I mean the transfer function and everything using Fourier transform. तो इसमें बस इतना ही read कर लो, बस ज़्यादा नहीं read करना है, okay? So system analysis using Fourier transform. So conceptually the Fourier transform can be used for analysis of relaxed LTI system. Okay, remember the system must be what? Relaxed LTI system. Relaxed LTI system, okay? ठीक है. So in case of time domain, if input is given, the impulse response is there and you have to find the output. So what is that? The output is going to be what? Suppose this is h of t and अगर ये मान लो तुम्हारा input xt है, then you have to find by of t. So what is by of t? Which is nothing but convolution xt convolve ht. But अगर हम Fourier transform की बात करते हैं, we have to find the Fourier transform of this guy x of omega. इसका क्या हो जाएगा h of omega and y of omega is gonna be what? The product, right? The convolution in one domain correspond to, okay, product in the frequency domain. Okay, I think everybody knows this from the property only. From the time domain only we are doing everything. In time domain we have to convolve, but suppose at times convolution is very difficult for you, right? Though I have simplified the convolution as well, लेकिन convolution मान लो difficult है, तो आप क्या कर सकते हो? x of omega, h of omega, then y of omega equal to x of omega and h of omega. ठीक है? So this is nothing but a what? This in f also you can write. So you know, देखो मैंने क्या लिखा? Y of omega equal to x of omega, h of omega. You can also write this as y of f equal to x of f, h of f. From here you can find the transfer function, right? So transfer function is going to be what? So the response by t of a relaxed LTI system. What is the meaning of relaxed LTI system? With zero initial condition, okay, whose impulse response is st to an input xt. So we will get the convolution, right? In frequency domain, this relation will translate to what? The product of the input x, I mean the Fourier transform of, okay. So I think this is clear for all, right? So this h of f, अगर आप यहाँ पर ऐसा लिखते हो by omega upon x of omega, so this h of omega, or you can say that by of f upon output upon input, right? Fourier transform of output upon Fourier transform of input. So this is known as transfer function. इसको हम लोग क्या बोलते हैं? Transfer function, right? Transfer function of relaxed LTI system. Okay. What is transfer function of relaxed LTI system, guys? Okay, that is, you have to remember the Fourier transform of output upon Fourier transform of input, right? So let me take this and show you the system input output relationship, okay, in frequency domain. So this is nothing but in time domain as well as the frequency domain. Okay? This is how it is related. ये input है. System, it is a system where the impulse response is given always st. The output can be computed using the convolution integral, and they are commutative, so you can write xt convol st or st convol xt. Output is nothing but convolution of xt and ht. Now if you take the Fourier transform of this, so you can also write x of omega or h of omega. So it is gonna be what? X of omega, h of omega, right? Okay, the product of that. Here we call it convolution, here we call it product. Okay. So this is nothing but a system input output relationship in the time domain as well as in the frequency domain. Okay. And then you can find out the Fourier inverse Fourier transform, right? So the transfer function is what? What is transfer function? Transfer function is nothing but the Fourier, the frequency domain description of the relaxed LTI system. Remember, the system must be relaxed. Okay, if you want to compute the transfer function, the system must be relaxed. Okay. So this is one of the important note point that you have to remember, right? What is transfer function? Transfer function is nothing but it is a frequency domain description of a relaxed LTI. This is an important line, relaxed. Okay. The transfer function h of f equals the transform of the system impulse response. It is also defined as this, the ratio of Fourier transform of output upon Fourier transform of input. Okay. So if suppose you have been given some differential equation of the form, right, you can say any relaxed system is given, uska for relationship is given in by what? Differential equations, right? Suppose any LTI system is described by the differential equation. Okay, so to the left hand side output will be there, to the right hand side input will be there. So you have to take the Fourier transform, and then if there is a derivative, so you have to use the property of differentiation, right? So you have to replace dy by dt by j omega. Okay, I hope this makes sense. तो मैं बस इसको directly यहाँ लिखूंगा. I don't have that much time. You just put this, okay, and you can make it into polynomial, right? So you see, ये आप directly समझ सकते हैं. So a relaxed LTI system is described by the differential equation of the form. So this is nothing but your nth differential equation, right? And mth here, right? So dn dy by dt. So what you have to remember is dy by dt is nothing but what? J omega or j2 pi f, right? You can replace it. Okay, so this is far easier, okay, in omega form. So you can replace these are the coefficients, right? The constant coefficients. Okay, in time domain I have discussed about this, the relationship between input and output described by the differential equation. So here we are taking the Fourier transform of that, okay, and the by omega and x omega, take the ratio to get the transfer function. Okay. for LTI system, the transfer function is the ratio of polynomial, right? So you can say this is nothing but a polynomial now. See, you have converted, okay, the differential equation into polynomials, right? Fine. So I think this is clear and it is only the fact, right? So there are three representation of relaxed LTI system. एक तो differential equation है, so you can take the output upon input, okay? Or you can also, I think this is clear, right? Okay. And if you want to get back the impulse response, what do you have to do? You have to take the inverse Fourier transform. That's it. Okay. So let me take the question here. Suppose we have got a signal of this kind. Suppose this is a question. And we have to find h of omega. So h of omega क्या हो जाएगा? So this is nothing but 1 plus j omega plus 1 by 2 plus j omega. But you have to simplify this. And if you're going to simplify this, right, so you can just simplify. I need not to. So 2 plus j3 omega plus j omega square, okay, 3 plus 2j omega, right? So this is the simplification here. You can take the LCM and then, okay. So I think this is clear, right? So in fact, in Laplace transform also you will do the same, right? So we have to replace, dy by dt by s, and s will be there the j omega. Okay. So in case of Laplace transform, I will talk about, don't worry, right? Transfer function कैसे निकालते हैं. In this case, what you can do here is, this is double derivative here, right? So this can be written as j omega whole square plus, 3j omega plus, okay, 2 times y omega equal to 2 times j omega plus 3 x of omega. Now you can take the ratio here, y of omega by x of omega. So 3 plus 2j omega by 2 plus 3j omega plus j omega square. I think same, right? Whatever we have got here, using this, the same, your input and outputs are described by the differential equation here, right? So you can find the transfer function. So this is one form, okay? So please remember this, okay? So I mean, they might give you the impulse response directly and you have to find the Fourier transform of it, or they might give you the differential equation. From differential equation you can find out the impulse response and then find out the transfer function. तो ये डिपेंड करता है, ये क्या है, दिस इज आल्सो एच ऑफ ओमेगा. तो आपको ये देखना है कि आपका सिस्टम जो है कैसे डिस्क्राइब्ड है, ओके. सो in fact you can also do like this, you can cross multiply and then you can find out the time domain, like differential equation back also, ठीक है. And basically we use transfer function concept in electrical circuits, right? So suppose any inductor is given, or you can say that, okay, so let me recall here the transfer function of the electrical circuit. Transfer function of electrical, circuits components, you can say. So suppose we have got how current and voltages are related by the differential equation in case of inductor. So VLT equal to L di by dt. So इसको हम कैसे लिख सकते हैं? You can write this as VL omega J omega L, right? And this is current I omega. So VL omega by IL omega, right, equal to J omega L. And this is nothing but the impedance, right? We call it impedance, ZL. ZL is nothing but what? Inductive impedance, which is J omega L, where XL is nothing but omega L. XL को हम लोग reactive, inductive reactance बोलते हैं. इसको inductive reactance बोलेंगे, इसको impedance बोलेंगे, ZL. ठीक है. सो आप ZL को ऐसा भी लिख सकते हो JXL, right? In phasors we use these concepts. ठीक है. In capacitor also you can recall, right? ICT equal to C dVC by dt. So IC omega equal to J omega C, right? VC omega. Now you can take the ratio VC omega by, since we want to define the impedance, that should be having the dimension of ohm. So this is nothing but 1 by J omega C. Okay, so this is the ZC. Or you can also see that XC equal to 1 by omega C. ठीक है. So your ZC is nothing but minus JXC. ठीक है. इसको बोलते हैं क्या? Capacitive reactance. In electrical circuit we will discuss all this. So these are the transfer function. In case of resistance, no problem is there, right? So ZR, ZC, ZL have the same unit. Okay, that is. So I think this is clear, right? So you can always convert your transformation of the electrical circuit elements, okay, to the frequency domain. कैसे करोगे ये? जैसे मान लो रेजिस्टेंस है, रेजिस्टेंस का रेजिस्टेंस ही होता है, there is no change. But suppose inductor is given, okay, so L in Henry, so J omega L, convert into frequency domain. C will be given in phasors. You have to do this, right? So C can be written as J omega C, or you can also write this as JXL minus JXC. ठीक है. Okay. Suppose you have got any electrical circuits. Let me take one circuit here. Suppose you have got RLC circuit, right? Time domain RLC circuit. I mean series RLC. ठीक है. एक क्वेश्चन लेते हैं. This is series RLC circuit. Okay, all circuit elements are connected in series, and you have to find the impedance, right? Impedance is nothing but ratio of what? The voltage upon current. Okay. So what you have to do? You have to first convert this into frequency domain, right? So you can convert into frequency domain. Okay. So I think this is clear, right? So how to convert? All the element has to be replaced by their frequency domain description. Okay. Because you know that in case of inductor as well as the capacitor, they are related by differential equation because they are the memory element, right? And memory elements are nothing but dynamic system, right? Oh, they store something, right? Capacitor stores charges and the inductor stores ठीक है, इलेक्ट्रोमैग्नेटिक एनर्जी. सो आप देख सकते हैं यहाँ पर. ठीक है, मैंने कन्वर्ट कर दिया. बस आपको क्या करना है फिर? यू हैव टू जस्ट अप्लाई 1 KVL एंड यू विल गेट द आंसर, राइट? ठीक है. So I need not to apply it because I haven't taught you. So now we have to discuss one more concept. So how to find the zero state response of the LTS system? Zero state response means initial condition is zero. The system is relaxed. Okay. Zero state response means zero state output you have to find. That is very simple. Okay. You have to find the Fourier transform, find the transfer function. Okay. That's it. I mean by f equal to product. That is what the zero state response. So zero state response निकालना है. That is nothing but what? This is zero state response. Please follow this technique. Simply you have to find the Fourier transform of input, then evaluate the transfer function from this ST, that is from the system equation or system equation, okay? And that is zero state response, zero state output you can see, and take the inverse Fourier. Okay? I hope this makes sense. Okay. So let me take one question here. So this is nothing but your system response, okay? System response bolo, zero state response bolo, right? Everything is same here, right? So this is a question. LTS system is described by h of omega. That is 4 by 2 plus j omega. Okay, so you can find out ST also here. Now find its response by t if the xt is this. So xt इसका फोरियर ट्रांसफॉर्म क्या होगा? 3/2 plus g omega. ठीक है. So what is bi of omega? Bi of omega is nothing but x of omega times h of omega. So x of omega is nothing but 3/2 plus j omega. You know, you have to take the product, right? H of omega is nothing but 4/2 plus j omega. Now you can multiply this, so it is nothing but 12/2 plus j omega by square. Okay? So I think you can identify this is here square, right? So you have to 100% what do you have to do? I think you can identify. So 12t, what is the inverse? So by t you can find out. So by t is the inverse Fourier transform of this, right? So that is 12t e raised to power minus 2 t ut. Okay. Yeah. So if you have attended this, so you can identify, right? I have told you all the concept. ठीक है. मतलब मैंने बताया था कि t, okay, t e raised to power minus at ut has the Fourier transform 1 by a plus j omega का होल स्क्वायर. अब मान लो यहाँ पर t to the power n है. What is the Fourier transform here? Then n factorial by j omega n plus 1. ठीक है. I hope this makes sense to you, right? So it is very simple to find out. Okay. But sometimes you have to also understand. Suppose you have to find the Fourier transform. Let me show you. Sometimes you can also find out using convolution also, despite they are asking like this. ठीक है. देखो. जैसे इस question में I think it is very simple to use the convolution, okay, instead of going to use Fourier transform and all, because it will take a lot of time. You know, the Fourier transform of ut is 1 inch long. ठीक है. So मेरा सजेशन रहेगा कि आप इसका टाइम डोमेन निकालिए, st निकालिए एंड डायरेक्टली कन्वोल्यूशन. आपको पता है कि किसी भी सिग्नल का अगर आप कन्वोल्यूशन करते हैं ut के साथ तो सिंपल इंटीग्रेशन हो जाता है. तो यू नो इट्स नॉट दैट डिफिकल्ट. सो फर्स्ट ऑफ ऑल यू कैन फाइंड आउट h of t. So h of, that is my, see in this case since ut is given, so avoid, right? Avoid, you can say avoid, you know, I mean using ft transfer function concept, right? Avoid transfer function. Okay, for the exam sake, because you know, let me show you also. St is nothing but, you know, what is the Fourier transform, inverse Fourier transform of this? 4 e raised to power minus 2t ut. Okay. Now you have to convolve with this. I mean, you have to find by t. So what is by t? By t is nothing but xt convolve ht. Now here xt is nothing but ut convolution 4 e raised to power minus 2t ut. Now you have to convolve any signal. Suppose this is any signal, any arbitrary signal with the ut. So आप क्या करोगे? So by t you can directly find now by integrating from, you know, since ut से convolution कर रहे हैं तो it will start from 0 to t, right? And directly integrate this 2 tau t tau. इसको इंटीग्रेट करने में आई थिंक बहुत टाइम नहीं लगेगा. सो इट इज नथिंग बट minus 2 e raised to power minus 2 tau from 0 to t. यहाँ पुट करेंगे तो इट विल बी नथिंग बट, you know, 2, okay, 2, you know, I think this is clear. 2 minus 2 e raised to power minus 2t times ut. ये आंसर है. तो विच मैथड इज सुटेबल फॉर यू, दैट आल्सो यू हैव टू डिसाइड. ठीक है, डोंट बी ब्लाइंड. अब देखो यहाँ पर आपको पता है कि फोरियर ट्रांसफॉर्म आपको पता है, यू कैन फाइंड, बट हियर ut का फोरियर ट्रांसफॉर्म इज 1 inch लॉन्ग, राइट? एंड देन यू नो डूइंग, you can check it out. I'm just going to show you the you know, the way in the book it is given, right? So you have to decide which is the method. Okay, let me show you. So in the book you can see my answer is this, right? ये है Fourier transform भी, right? Alternate, but I don't recommend it for the exam. ठीक है, देखो कितना बड़ा है. So आप बोलोगे आपके, हाँ धीरज सर आप सही बोल रहे हैं. ये ठीक है, देखो कितने स्टेप हैं, 1 2 3 4 5. लेकिन ये सब करने में ना बहुत टाइम लगने वाला है. यू सी ये यूटी का फोरियर ट्रांसफॉर्म, राइट? आई मीन 1 by j omega plus pi delta omega, that is u of omega. If you do in omega domain, but they have done in f domain, right? See, answer is that only. So आपको डिसाइड करना है कि कौन सा मेथड अच्छा है. ये मेथड नहीं अच्छा है इस केस में, जब ut input is ut simple, right? Simply go for convolution, right? One line answer. Don't get ठीक है, okay. So I believe this is fine. Now we will talk about, sir, steady state response to harmonic inputs, and this is one of the important concept, right? In each year you will find one question, right? How to find the steady state response to any harmonic input. Harmonic input means if input is cosine or sinusoidal or exponential, it's like a eigenfunction concept, right? So if input is sinusoidal, cosinusoidal, right? So output will also be cosinusoidal, sinusoidal, right? Exponential. बस उसमें changes क्या आएंगे? The phase and the magnitude, right? That will be changed. Okay, so magnitude has to be found out from the impulse response, okay, by finding the frequency response, okay, and then find the magnitude at the input frequency, okay, and find the phase also, and then multiply the phase, sorry, multiply the magnitude with the input and add the phase. ठीक है, बस इतना ही है. So finding steady state response of the LTS system to sinusoidal input, okay, ये बहुत इंपॉर्टेंट टॉपिक है. देखो, input is this, output will also be same, but this a will not be there. A times something will be there, right? So you have to evaluate the transfer function h omega at input frequency. This is the input frequency, guys, at input frequency, like this. Okay, you have to find k and you have to find phase. K is nothing but the magnitude you have to find of this, and then multiply. See, multiply with k and add the phase. This is the steady state output. Okay, I hope this makes sense. तो इनपुट अगर आपका साइनोसॉइडल है, साइन ओमेगा टी, कोसाइन ओमेगा टी, e raised to power j omega naught t, so output will also be the same. This should be h of omega. I mean, you have to find h of omega by finding the Fourier transform, and this will give you, by t. This is nothing but steady state analysis. So remember, the amplitude has to be multiplied by some constant k, right? You have to find the k by finding the magnitude, and phase has to be added, right? So let me take one question so that you can understand. हर साल एक क्वेश्चन आता है, ठीक है? This is a question. Here they have directly given the Fourier transform, but sometimes what they do is they don't give the Fourier transform h of omega, they will give st. So आपको Fourier transform निकालने में कोई difficulty नहीं होनी चाहिए if you have got enough practice and you have seen my lectures, right? You have watched my lectures carefully, ठीक है? So h of omega is nothing but this, okay? I hope this makes sense. So you can find out the Fourier, what is yeah, that is fine. So you don't have to find inverse and all, right? Since input is this, so I can directly write output by SST is going to be 3 times k sine 2t plus 5. I can write answer. This is the answer. Now what is your job? Your job is to find k, guys. What is this k? This k is nothing but h of omega, mod of h of omega at omega equal to omega naught. So what is mod here? So you can take 2 common, right? So it is nothing but 1 by square root of 1 plus omega square, right? And put omega equal to omega naught, which is nothing but 2. You can see this is the input frequency omega naught. So इसमें रखेंगे तो 1 by 1 plus 4, which is 1 by root 5. ठीक है? And the phase you can find out. Phase is nothing but what? Tan inverse minus tan inverse, right? Because h of omega कितना दिया है? You can just forget this 4, right? So you just write 2 here. I think there should be 2 as well. I forgot 2, right? So you have to write 2 here. यहाँ 2 होना चाहिए. This is 2, right? क्योंकि 2 cancel हुआ ना. And this is 1 plus j omega. Now you have to find phase. Phase is going to be minus tan inverse, because the denominator it goes up, so minus tan inverse imaginary part omega at omega equal to 2. So tan inverse 2. You don't know the value, it's fine. I mean, if you know the value, I mean, I think 1 minute. Yeah. 1 minute. Let me check it out. Something is missing here. Yep. I think here you have to be little careful, right? Yeah, while finding the phase. Okay. So what we can do here is if you take 2 out, 4 by, yes, that is fine. Okay. So you have to find the phase at what? You have to find phase at, okay, at omega. ठीक है, तो ये सही है फिर. I was thinking there is some error, but in the book itself there is error, right? They have done some mistakes. Okay, so please be careful about that book also, right? If there is a mistake. ठीक है, तो ये प्रोसीजर आपको क्लियर है ना? You can find out this. ठीक है, okay, fine. So be careful. Okay, sometimes they also make mistake. So how to find the steady state response? This is the way, right? So if you want to find the total response, I mean, suppose you know the total response and you have to find the steady state response. So what you can do, you can drop the transient term and the remaining is going to be steady state response. So this comment also you have to remember. One comment I'm just going to. क्योंकि मैंने ये बताया है टाइम टेबल, राइट? सो the formal alternative is to find the total response and then drop the transient term. This method is not only tedious but also requires a product property of impulse for simplification of the result. So stay away from the alternative if all you need is the steady state. So आपको steady state response find करना है, so then forget about transient response, right? Directly you can use this concept and find out. Okay, so don't go to total response and all, right? Okay. And you have to also understand the frequency response of the filter, guys. Sometimes this frequency response h of omega is treated as a filter. Your LTI system is treated as a filter. Frequency response of filter, right? Frequency response of filter, please remember. ठीक है, so the frequency response, we call it h of omega. H of omega is nothing but a frequency response, represents the transfer function for harmonic input, and it is useful primarily for the stable system. Okay, remember, for a stable system, okay, If the system is not stable, then there is a problem, right? So for stable system, we talk about frequency response whose natural response decay with time, right? Yeah. Okay. And this you can say this frequency response also have the conjugate symmetry, right? So if you replace omega by minus omega, so you can take the conjugate of that, right? And we also call, suppose we are finding the magnitude of the frequency response, we call it magnitude or the gain, and which is even symmetric of omega. And in case of theta, that will be what, the odd symmetric. So ये कुछ statements हैं जो आपको read कर लेना है, ठीक है? You have to follow the strictly the book here. So कुछ भी नहीं है इसमें. You can read it. The frequency response h of omega represents the transfer function for the harmonic and the DC input, and is useful primarily for a stable system whose stable system का मतलब क्या है? The system whose natural or you can say transient response does indeed decay with time. For a TI system, h of omega is nothing but what? The ratio of polynomials in g omega. That is h of omega equal to pi omega by x of omega. ठीक है? And possesses or have the conjugate symmetry. Conjugate symmetry का मतलब h of minus omega is h conjugate omega. It is nothing but a magnitude or a gain and is even symmetric. आपका जो gain या magnitude होगा even symmetric with omega, and the phase is gonna be odd symmetric. खत्म. ठीक है? I think this is clear. Okay. Okay. So what you can do here is there will be two things that you have to remember. So what is filter? If I ask what is filter, so filter is nothing but a frequency. Filter is going to be what? The filter is going to be what? It will pass the certain range of the frequency and it is going to block the rest. Okay. So there are different types of filter like low pass filter, right? So it is going to pass the low frequency, range of low frequency, and it is going to reject all the high frequency guys, right? And if it is a high pass filter, it is going to pass the high frequency and then block the rest. Okay. And if it is a band pass filter, so it is going to pass the band of the frequency and reject the low and the high. Okay. Band stop अगर है तो मतलब different types of filters are there that I will discuss in an network theory as well as in analog, but यहाँ पर अभी आपको बस थोड़ा बहुत समझ जाना है, right? So okay, so band edge frequencies are nothing but cut off frequency. ठीक है? तो मान लो जैसे h of omega ऐसा क्वेश्चन में दिया है, ऐसा h of omega, right? Sometimes it is given. So मान लो ये दिया है 2000 pi से लेके 2000 pi, right? So this frequency is known as cut off frequency. ये क्या है? Band edge frequency. इसको हम लोग क्या बोलते हैं? Cut off frequency, right? R this is band limited here, right? So we call it cut off frequency. ठीक है? And the range of frequency what the filter can pass defines the pass band. Okay, the range of frequencies which are blocked defines the stop band. तो आपको कुछ इस टाइप के वर्ड्स मिलेंगे, पास बैंड, राइट? पास बैंड मतलब जो फ्रीक्वेंसी पास होती हैं, स्टॉप बैंड, राइट, जो ब्लॉक्स हो जाती हैं फ्रीक्वेंसीज, रेंज ऑफ फ्रीक्वेंसी, नॉट द सिंगल फ्रीक्वेंसी, रेंज ऑफ फ्रीक्वेंसी. And the band edge frequencies are called cutoff frequency. So ideally a filter should have a perfect transmission in pass band and perfect rejection in stop band. The perfect transmission implies a transfer function, right, with a constant gain and linear phase over a pass band. ठीक है? So if the filter has constant gain मतलब 1, you can say constant gain 1, and the output is an amplitude scaled replica of the input. Okay, the ठीक है, अगर मान लो ये कांस्टेंट है तो आउटपुट विल बी इक्वल टू इनपुट ओनली ना, क्योंकि the band, the h omega is constant, right? So if you see there, right, so that is going to be 1, right, because pi of omega will be equal to x of omega. ठीक है? I think this is clear, right? Similarly, if the output undergoes a linear phase shift with frequency, okay, so output is time shifted replica of the input. Okay, ठीक है? So if the gain is not constant over the required frequency range, then क्या होगा? मान लो अभी यहाँ पर गेन क्या है, कांस्टेंट है, ठीक है, तो आउटपुट आपका एग्जैक्ट रेप्लिका ऑफ द इनपुट है, सेम, क्योंकि ये तो 1 है ना। लेकिन मान लो अगर आपका जो पास बैंड है h of omega in the range of frequency, it is not constant, right, it is changing, so there will be amplitude distortion. Okay, what we call it, amplitude distortion. आपको इस तरह के वर्ड्स सुने होंगे, amplitude distortion. So amplitude distortion कब होता है? जब जो आपका पास बैंड है, ओके, इट इज नॉट कांस्टेंट ओवर द रेंज ऑफ द फ्रीक्वेंसी, राइट? ठीक है, एंड द फेज इज नॉट लीनियर। तो देखो परफेक्ट ट्रांसमिशन का मतलब क्या है, कांस्टेंट एम्पलीट्यूड, कांस्टेंट गेन एंड द लीनियर फेज। ठीक है, दैट इज अ परफेक्ट ट्रांसमिशन। परफेक्ट ट्रांसमिशन means h of omega must be constant, right, and the phase of this must be linear function of omega, linear function of omega. ये परफेक्ट ट्रांसमिशन हर जगह पॉसिबल नहीं होता, राइट? ठीक है, so if the gain is not constant over required frequency range, that is called as amplitude distortion, and the phase shift is not linear with frequency, so we will call it phase distortion. Okay, if there is a phase distortion, so signal undergoes different delays for the different frequency. ठीक है, अगर मान लो फेज डिस्टॉर्शन है, ठीक है, तो सिग्नल will undergo different delays for different frequency. So those delays are important, and those delays are known as what? The phase delay and the group delay. So in the exam आपको फेज डिले भी कंप्यूट करने के लिए आएगा। फेज डिले क्या होता है, ग्रुप डिले क्या होता है, अब आपको समझ में आना चाहिए कि फेज डिले और ग्रुप डिले का कॉन्सेप्ट कहां से आया। The phase delay and the group delay concept is coming because of the phase distortion when the phase is not the linear function of the omega frequency, you can say. When the phase is not linearly changing with frequency, so there will be a phase delay. So there in the system there will be different phase, okay, different delays, right, for different frequencies, right? So बस इसको मैं यहाँ पर कट करके लगा देता हूँ जिससे आप समझ जाना। ठीक है, जो मैंने अभी आपको बोला है, तो यू कैन जस्ट रीड इट, दिस थ्योरी। And I have shared the book as well, so you can go through that. But needless to go through if. So again, let me go through. This is important line. Everything is highlighted. A frequency selective filter is a device that passes a certain range of frequency and block the rest. The range of frequencies passed define the pass band, and the range of frequency blocked defines the stop band. The band edges frequency are called cutoff frequency. Ideally, a filter should have perfect transmission. देखो perfect transmission का मतलब क्या होता है? In the pass band and perfect rejection in the stop band. तो perfect transmission का मतलब क्या है? Transfer function with constant gain and the linear phase over a pass band. Okay, I mean the phase must be changing linearly with omega. ठीक है? Straight line. Right. And if the filter has constant gain and the output is amplitude scaled replica of the input, okay, output is gonna be amplitude scaled replica of the input. मतलब your amplitude can be scaled by some constant, okay, like if h omega is 5 6 something, other than 1 as well, okay, but input will be same as output. Similarly, if the output undergoes a linear phase shift with frequency, the output is going to be time shifted replica of the input. Okay, yeah, certainly that we know, right? If there is a phase change in the in the frequency domain, it means there is a shift. Okay, there is a shift in the time domain. Time shift correspond to phase shift. Okay, that I have told you, right? So confusion नहीं होना चाहिए. If the gain is not over required frequency range, so we have amplitude distortion. If the phase shift is, ये important है. So we have phase distortion that is going to introduce different types of delay for different frequency, right? Okay. So how to find the phase delay and the group delay? Phase delay and group delay. ये भी क्वेश्चन आता है आपके एग्जाम में. So suppose you have got a transfer function h of omega. From the transfer function, what you can find out? You can find out the magnitude, or you can say the gain and the phase, and then decide whether there is a phase delay or not, right? So or group delay कैसे find करेंगे, right? So ठीक है. तो जैसे ही आपको थीटा ओमेगा आ गया, so theta omega has to be, if you want to find the phase delay, so phase delay is defined like this: Tp equal to minus theta omega by omega, right? This is nothing but a phase delay. Simply you have to divide that theta omega by omega, that will give you the phase delay. And if you want to find the group delay, so you have to differentiate this guy, right? Minus sign के साथ, ठीक है? So your group delay is going to be what? Tg is going to be minus d phi omega by d omega. This is a group delay. Okay, and this is the phase delay. But you have to find what? You have to find the angle first. Okay, so theta omega varies linearly with the frequency t. Okay, and Tp and Tg are not constant but also equal. Please remember, right? Okay, so remember they are not equal also. Tp and Tg both are not same and they are not constant as well. Okay. So for LTI system with rational transfer function, the theta omega is a transcendental function, but the group delay is always a rational function of omega square. Okay, and it is very simple, easier to work with in many filter application. ठीक है? So I hope this makes sense. ठीक है? So let me also show you something here, जो आपको अपने शॉर्ट नोट में लिख लेना है. तो ग्रुप डिले मीन्स ग्रुप ऑफ फ्रीक्वेंसी और फेज डिले मीन्स सिंगल फ्रीक्वेंसी. ये याद रखना. ग्रुप डिले क्यों बोल रहे हैं? ग्रुप ऑफ फ्रीक्वेंसी इन अ सिग्नल. So phase delay is Tp equal to minus theta omega by omega. Theta omega कहाँ से निकालेंगे? आपको h of omega से मिलेगा. That this is a delay at single frequency. जैसे मान लो तुम्हारे पास cos omega t और यहाँ phase shift है Tp, you can say. You can write this as cos omega t minus omega Tp, right? So you can just say that this is theta equal to what? Omega Tp. So Tp equal to minus theta by omega. So see, there is a phase shift, and I hope this makes sense, right? So there is a time shift and we are getting the phase shift. Group delay का मतलब क्या होता है? Delay for group of the frequency in a signal. ठीक है? And if there is an ideal filter means filter transfer function with constant gain and linear phase. Ideal का मतलब होता है there is no distortion, guys. No distortion, no amplitude distortion, no phase distortion. Okay, ideal का मतलब यही होता है. Ideal filter का मतलब होता है कि distortion less. Okay, distortion less. So ideal filter का मतलब क्या होता है? Distortion less. Okay, filter. No distortion, no phase. I mean, the gain is going to be constant over the range of frequency. Phase is going to be the function of linear function of the frequency, right? All okay. ठीक है. So you will get ideal the transfer function for the low pass filter, okay, and impulse response, okay. So transfer function or frequency response in time domain we'll call it impulse response of ideal low pass filter, right? Okay, with the unit gain and zero phase cutoff frequency is gonna be fc, right? So suppose I'm just going to draw it. देखो ये तुम्हारा क्या है, h lpf you can say 1 ओमेगा सी, ये ओमेगा सी है, दिस इज नथिंग बट योर ओमेगा, ठीक है? आई थिंक दिस इज क्लियर, राइट? सो यू कैन फाइंड द एच ऑफ एल पी एफ, क्या हो जाएगा ये, साइन ओमेगा सी टी बाई पाई टी। इसको आप सिंक में भी कन्वर्ट कर सकते हो, ठीक है? सिंक में कन्वर्ट करेंगे क्या हो जाएगा, इसको सिंक में आप कन्वर्ट कर सकते हैं, राइट? तो ओमेगा सी से मल्टीप्लाई कर सकते हैं तो सा में कन्वर्ट हो जाएगा, एंड इट्स वेरी सिंपल टू राइट, ओके? So it's a very simple situation that you can do here, okay? So इसका फोरियर ट्रांसफॉर्म यही होता है, ठीक है? इसको रेक्ट में भी लिख सकते हैं। So ये आइडियल है। आइडियल का मतलब क्या होता है सर, अब फिल्टर ट्रांसफर फंक्शन विद कांस्टेंट गेन एंड लीनियर फेज, ठीक है? तो आपको चारों टाइप के वो मिल जाएंगे, मैं बस आपको शो करना चाहता हूँ। The spectrum of the ideal filters they have given in in f form, you can convert into omega just by multiply 2 pi। इसको अगर आप ऐसा लिखना चाहते हो तो this is minus omega c and this is omega c is 2 pi f। low pass, high pass, it does not pass low frequencies, band pass, so इसमें okay, and this is called band stop, right? Band stop, okay, ठीक है? बट एक प्रॉब्लम होती है आइडियल लो पास फिल्टर के साथ, ठीक है? सी आइडियल लो पास फिल्टर इज नॉट आइडियली रियलाइजेबल, राइट? एंड आइडियल लो पास फिल्टर इज नॉन कॉजल एज वेल, ठीक है? तो बहुत सारी चीजें जो आपको समझना है। सो आइडियल, व्हाट आर द कैरेक्टरिस्टिक ऑफ द आइडियल फिल्टर्स, राइट? ये आइडियल फिल्टर्स हैं, बट आपको लगता है कि आप इस तरह डिजाइन कर पाएंगे? प्रैक्टिकल शुड बी लाइक दिस। ये शार्प एजेस आर द प्रॉब्लम, राइट? ठीक है? So ideal filters are non-causal, unstable, and physically unrealizable. We can't physically realize it. Ideal filter have constant gain, linear phase in pass band. You can see all the filters that I have shown here. All the filter has constant gain, right? ठीक है? तो एग्जाम में यही आता है, इतना डिफिकल्ट नहीं देगा, डोंट वरी। Their impulse response, their impulse response with the sync form makes them non-causal and unstable. Yes, the step response of the ideal filters cannot be monotonic and shows overshoot and ringing. Okay, if you find the step response and all, right? So you can also get RC low pass filter, that is single time constant filter, right? You can find out, and it's its transfer function also you can find out, right? That is very simple. You can find out the, so I think it is very simple to find out, right? 1 by 1 plus j omega RC, ठीक है? And then magnitude you can find out, and phase you can find out, right? Simple, ठीक है? So आज से याद रखना, क्या याद रखोगे कि very important to keep in mind, right? Okay, take circuit, take filter, take LTI system as a filter। टाइम डोमेन में कर रहे हो तो इम्पल्स रिस्पॉन्स है, जैसे मान लो ये रिस्पॉन्सेस हैं, राइट? आपको पता है अगर इनपुट में इम्पल्स रिस्पॉन्स दोगे, इनपुट में इम्पल्स दोगे तो आउटपुट आपका एक्सपोनेंशियली डीके आता है। ये इनपुट में अगर इम्पल्स दोगे तो ये आएगा रिस्पॉन्स, स्टेप दोगे तो आपका ये आता है। ये बहुत सिंपल है, मैंने बहुत बार बताया है। नेटवर्क में तो फिर से बताया जाएगा, लेकिन अभी ये आपको पता होना चाहिए कि इनपुट में अगर इम्पल्स दे रहे हो तो इम्पल्स करंट, ओके, जब जैसे इम्पल्स आप आफ्टर टी इक्वल टू जीरो, ग्रेटर देन जीरो, it becomes source free circuit, right? Okay, it becomes source free circuit, then your capacitor will discharge through, understand? तो ठीक है, तो आप बुक से देख लेना जो भी है। Okay, the frequency response of low pass filter is the time constant is going to be RC, and everything you can find out, right? ठीक है, fine. So this is over, guys, and now I mean we have discussed this filter part, or let me check और कुछ है क्या? Yes, so I think this is over. ठीक है, yeah, everything we have discussed, right? So like power spectral density and all we will discuss, okay, in the introduction part of the communication system or in detail only random process में, ठीक है। बाकी आपका Fourier transform over हो चुका है। Now you can practice all the questions from PYQ, ठीक है। Thank you so much, we'll meet in the next session. You guys can practice question from Ambarder. Question from Ambarder and PYQ of EC, EIN, right? Enough. Thank you.